Hi, I'm Joseph. Today I'm going to talk about analog to digital converter. See, many of the sensors we use, they give the analog input, and microprocessor and microcontroller which are going to process the signals, they require the digital input. So is the need of analog to digital converter. This is also called digital to analog converter. Now we're gonna talk about only analog to digital converter. Before that, what is analog signal? How does that look? It just looks like this. It's like a random signal kind of. And what does a digital signal look like? It looks like this, like lows and highs, or you can say that zeros and ones. The low is 0, high is 1. Okay, they only have this digital signal only have two states, that is low and high. Now when we consider a system using two state signals, it allows the application of Boolean logic as well as binary number representations. So in analog signal changes are continuous, whereas in digital signal exists only at two specific levels. So states changes its level in discrete steps. These are discrete steps. Where it is continuous. So this is continuous, changes continuous. Here the changes in discrete steps. So now we consider a digital signal. The output from most sensors tends to be in analog form. So the size of the output being related to the size of the input. A microprocessor or microcontroller is used as a part of measurement or control system, and it can take only digital signals. So the analog output from the sensor has to be converted to digital form before it can be used as a input to microprocessor. That is twin, we're gonna use A to T converter. Likewise, most actuators operate with analog inputs. So the digital output from a microprocessor has to be converted into an analog form before it can be used as an input by the actuator. So again we're gonna use as digital to analog converter between microprocessor or microcontroller and actuator. Between this we're gonna use DNA, because this is gonna come as we get digital input to microprocessor, digital output will come, and this digital output should again be converted into analog in order to give it to the actuator. So here's the need of a digital analog to digital converter, and here's the need for digital to analog converter. Now we talk about Binary system. It is based on two symbols or states 0 and 1. There possibly be 0 volts, that is for 1, and 5 volts for being for 1. Let's like this is low, this is high. So 0 and 1 are termed as binary digits or bits. Digital position in number indicates the weight attached to each digit. Like I said, high and low. Weight increases by a factor 2 as we proceed from, say, consider 2 per 0, 2 per 1, 2 per 2, 2 per 3. This is for bits 0, whereas this is for bit 3. So as continues from right to left, the weight increases by a factor of 2. Example, the decimal number, if you consider 14, what is the decimal number? Considers 14. Let's say 2 to the power of, let's say like this, you can say 8, 4, 2, 1. Say to the power 0, and we need 14, right? 2, 4, wait, 8 plus 4, 12, 14. So you're gonna get like this 1, 1, 1, 0. So it will be like 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3. You get it? It's like this. The combination of bits to represent a number is a word. Thus, 1110 is a 4-bit word. Such a word could be used to represent the size of the signal. So the term 1 byte is equals to 8 bits. Let's consider a decimal equivalent to the binary equivalent. Let's say it's for 0, for 0, 0, 0, 0, right? Now it's for 1. If you consider for 1, there's just a shortcut like 8, 4, 2, 1. For this, how we're gonna represent for 1. For this is gonna be a 1, and rest of things we can consider zeros. So 0, 0, 0, 1. To consider this, it's like 0, 1, 2 to 0 plus 0 plus 0. It's like this for this. And if you consider for 2, 8, 4, 2, 1. For this, for 0, it's 2 to the power of 0. Sorry, 2 to the power of 1. It is again 0, 0. And consider as what? 0, 0, 1, 0. 2 to the power of 1, 2, right? That's a high. For a high, if a number just exists, that's a high. If it doesn't exist, is 0, low. So 0, 0, 1, 0 is 2. Likewise, you can go till how many bits we needed. Now we consider analog to digital conversion. Analog to digital conversion involves converting analog signals into binary words, right? Like we said, this binary, what do you say? Digital position in number indicates the weight attached to each digit. So we can say it as converting analog signals into binary words. A clock supplies regular time interval signal pulses to the analog converter, and every time it receives a pulse, it samples the analog signal. Let's say we need a sample and hold device. Here we give the input as analog signal, and this we again give analog digital converter. We can get the output as digital signal, that is in binary words. We need to see, right? That's the reason we need to get into digital words. Now we consider a simple analog signal over time. Say it's like this, right? The clock signal supplies the time signals at which the sampling occurs. This is the signal. This, let's say, is a clock signal. Say occurs time like this. It's like this. The result of a sampling is a series of narrow pulses. Let's say it's like this. Go like this, right? Sorry, I just didn't draw in symmetric way. Let's say consider it's at a distance like this. How does it look when you combine it? It looks somewhere like this. Over the time, what this is called as sample signal. It's called sampling signal. The result of sampling is a series of narrow pulses. The sample and hold unit or device is then used to hold each sampled value until the next one occurs. You get that, right? It's gonna hold the each sampled value till the next one occurs. It's like this. This is just the representation. How a digital signal looks like is till, first of all, this is the same thing. It happens. First it will hold. The sample and hold unit or device, sample and hold device is then used to hold each sampled value. This is a sampled value, right? It will hold till the next eye occurs. Based on this eye occurred at this point of view, at this point. So till the next signal occurs, it's gonna hold this, and then this occurs. See, and again likewise. It's gonna be the same process. The sample and hold unit is necessary because analog to digital conversion requires a finite amount of time, that is conversion time, to convert the analog signal into digital signal. That's the reason why we use sample and hold device. Analog converter is an electronic device that converts analog voltage to digital code because we needed that. The output to the analog converter can be directly interfaced to digital devices such as microcontrollers and computers. Analog to digital conversion. It involves two things, that is quantizing and coding. See, in simple terms, what is quantizing, what is coding is, quantizing is the transformation of continuous analog input into a set of discrete output states, that is continuous to discrete, like this to like this, like this. And coding is the assignment of digital code word or number to each output state. For this, in order, we need to read, right? We need to take it as a value, not just a visual representation. In order to write it down, note it down, and read as well, we need a digital code word or a number. Okay. The resolution of AD converter is the number of bits used to digitally approximate the analog value of the input. It's like same thing, right? Why we said digitally approximate the analog value of the input in the sense is, for this signal we just use the clock signal to digitally represent it. We are not taking the exact values, like see how this is going. We're just taking a representation like this. No, here it was little high and it was in little high and now little low and completely low and then it went down. This is called approximating the analog value of the input. The number of possible states n is equal to the number of bit combinations that can be opposite from the converter, that is n is equals to 2 to the power of n, where this n is the number of bits. For example, 3-bit device as 2 to the power of 3, and or you can say 8 bit states. The opposite states are usually numbered consecutively from 0 to n to the power of 1, that is 0 to 7 in this case. Most AD converters are 8, 10 or 12-bit devices that resolves is in nothing but a sure one. Resolves 2 to the power of 8, 2 to the power of 10, 2 to the power of 12 or 256, 1024, 4096 states. Okay. The analog quantization size, that is Q, sometimes called the code width, is defined as the full scale range of the analog to digital converter divided by the number of output states, that is size Q is equals to V maximum minus V minimum divided by n. It is a measure of analog change that can be resolved by the converter. The number of analog decision points that occur in the processing of quantization, that is n minus 1, that is 7 in case of 3-bit device, that is 7 in the sense 0 to 7, totally 8. It is 8 states, 3-bit devices. Consider a 3-bit device which has 2 to the power of 3 or 8 output states are listed in the first column. The output states are numbered from 0 to n minus 1. The corresponding code for each output state is listed in the second column. That is, the decision point occurs at 1.25 volts, 2.50 volts, and 8.75 volts. That is, then code width Q is equals to V maximum minus V minimum divided by N is equals to 10 minus 0 divided by 8 is equals to 1.25 volts, which means the amplitude of the digital signal has an error of at most 1.25 volts. Therefore, the analog converter can only resolve a voltage to within 1.25 volts of the exact analog voltage. Okay, for example, a 3-bit device is like this. For 0.00, so 1.25 volts, and when we again add it, here 1.25, we get 2.50, and we again add it for here to next I, it's like this. So this over each bit 1 2 3 4 0 1 2 3 4. These voltages are called discretized analog voltage ranges. Then we get to Shannon's sampling theorems, which states that sampling rate of a signal should be more than 2 times the maximum frequency component in the signal to retain all frequency components. In other words, to represent the analog signal, the digital samples must be taken at a frequency such as that sampling frequency is greater than 2 into maximum frequency. It should be greater than, sampling frequency should be greater than 2 times the maximum frequency of the signal. Now, where Fmax is Nyquist frequency, that is the highest frequency component in the input analog signal. Time period between digital samples is delta t is equals to 1 by Fs, that is inversely proportional. If the sampling rate is like, let's say, 5000 Hertz, time interval between samples would be, this is the sampling rate, time interval between samples would be 1 by 5000, that is 0.2 seconds. Now, as I said, this is the thing that should be. What if the signal is sampled at less than 2 times its maximum frequency component? Then something occurs named as aliasing. 12 equally spaced samples are taken over 10 cycles of the original signal. Therefore, the sampling frequency is 1.2 f0, where f0 is the frequency of the original sine wave. Because the sampling frequency is not greater than 2f0, it will not capture the frequency in the original signal. It's like, let's say, this is an original signal. Okay. Now we consider as sample points. Okay, here in the signal itself. That is, therefore, undersampling not only results in errors but also creates information that is not true. Okay. This is alive signal. This is not there, it just shows that it's there because the frequency is less than. The sample is signal is sampled less than 2 times its maximum frequency component, then aliasing occurs. See, this is what it is. It is not there, but it's just when the frequency is less than this occurs, aliasing occurs. Between the sensor and the, as we seen earlier, between sensor as well as the analog to digital converter, the components used are there will be a buffer amplifier to amplify the signal in order to go through the low pass filter, and then it goes with sample and whole device, and from analog to digital converter we need to give it as to a computer memory. Let's say sensor, the signal is something like this. When we amplify it, it becomes clearer, and then low pass filter, the signal will become more clear, and to sample unit it will give a digital representation like this. It will take steps like this. And then a computer memory in the name of like this 0010 or something 0010000001. Likewise, this is a component. The buffer amplifier isolates output from the input, that is, it draws negligible current and power from the input and provides a signal in a range close to but not exceeding the full input voltage of the AD converter. And the low pass filter removes any undesirable frequency. This is the clearer image. This frequency, right? This frequency is not appearing here. So it removes the undesirable high frequency components in the signal that could produce aliasing. You avoid it. That's the reason low pass filter is used, to avoid aliasing. The cutoff frequency of the low pass filter should be no greater than the half the sampling rate. The sampling and hold amplifier maintains a fixed input value from inserted sample during the short conversion time of the AD converter. This converter should have a resolution and analog quantization size appropriate to the signal system as well as the signal. The computer must be properly interfaced to the analog converter system to store and process data, because every time we can't remember the signal, right? That's the reason we use the storage. So the ID system components described above can be found packaged in a variety of commercial products called data acquisition DAC or DAC or DAQ cards or modules. DAC products are available in a variety of form factors including PC, instrumental plan, plug-in cards, laptop, computer, PCMI cards, etc. Okay. The analog to digital converters. The input to an analog to digital conversion is an analog signal, as well as the output is a binary word that represents the level of the input signal. So these are designed based on number of different principles, where there are various principles like successive, approximation, flash or parallel encoding, signal slope and dual slope integration, switched capacitor, delta sigma. We'll talk about successive approximations. Successive approximations, just a representation will be like this. We'll take an analog input and we give it to a comparator, and this will be given to a gate. Gate is nothing but controls the admission of the pulses to storage register, and for this we are given a clock, right? And this we are now the digital, as we said, this gate controls the admission of pulses, that is input pulses to storage register, that is digital storage register, 4-bit storage register, like this, right? What's this called? 2 to the power of 3, 8. This is 8. Let's say this is a high, right? And this is the digital output, analog input to digital output. Then why we call it as approximation C-square? Again we give this to a DAC, that is and a digital to analog converter. These digital signals are given to digital to analog converter, and the analog output is compared with the initial analog inputs. So when we compare this analog input, that we get from analog digital to analog converter to the original analog input, we can see if it matches, the signal is right. So that's the reason, as this is a comparison again through the digital to analog converter, these are called successive approximations. We will be keep on doing this. This signal is again converted to analog, this signal is again converted to analog, this signal is again converted to analog. So each signal is compared to the initial analog inputs in order to check whether it is the correct in order to check whether it is the correct digital signal that we converted to digital. Okay, that's it. Okay, a voltage is generated by a clock emitting a regular sequence of pulses which are counted in binary number. Resulting binary number is converted into analog voltage through analog converter, this one. This voltage rises in steps and is compared with analog input voltage from the sensor. This is the input we get from sensor, initial input. When the clock generated pulse voltage passes the input analog voltage, the pulse from the clock are stopped being counted by the gate. Output of the counter at that time is the digital representation of the voltage, while the comparison could be accomplished by starting the count at 1, the LSB, and then proceeding bit by bit upwards. A faster method is by successive approximations. As I said, this is what we call as successive approximation. It's like approximating the output digital value through again a digital to analog converter with the initial analog input signals that came from the sensor to check whether it is the right one. When matches, it's right, otherwise it's not. That's the reason this is successive approximation, one of the successful method to used in analog to digital converter. This is the principle, successive principle. Okay, thank you.